All right, it is a mere 10 seconds after the previous video, and I am now going to do example 3, the ladder problem. I need to warn you, of all the problems encountered by first year physics students in a college curriculum, the ladder problem is considered one of the most difficult. There's a lot of details to take into consideration, a lot of different moving parts, but it is a real problem. It is a real thing. Ladders are a very dangerous thing in the home. And I'm not necessarily talking about those A-frame ladders that you pull apart, but the kind of ladder that you extend and then you just lean it against the wall of your house, and it has rungs. Now, this particular example is going to be very specific. First of all, I'm going to lean this thing at a 60-degree angle. That means up here is a 30-degree angle. And I'm going to have a frictional coefficient on the ground of 0.5. And there will be no friction where it leans against the wall. This is realistic because at the bottom of most ladders are a pair of feet that have rubber pads on them to increase friction on the ground. And the top of the ladder usually has a plastic cap on it to prevent it from marring the wall of your house, and that often doesn't have a lot of friction. So these are reasonable assumptions. This ladder is going to be 8 meters long and is going to have a weight of 25 kilograms. It was 20 in my previous example, so I'll be working with all new numbers. That's going to be exciting. All right, so this is a difficult thing. I want to know, basically, will it slip? So that's the question. Well, so let's get started here. Let's do an extended body diagram for the ladder. I'll square off the ends of the ladder to make it easier to draw. And we need to figure out what the forces are going to be on this ladder. Well, one that most people identify right away is the weight of the ladder. I'll call it M times G here. That's at the center of the ladder and pulling straight down towards the center of the earth. You know, I need a bigger drawing. I'm sorry about this. We need a bigger drawing. We're going to need a bigger boat. Okay. M times G. At the bottom, there's going to be a normal force upwards. Friction will go to the right. That's because the bottom end of this ladder wants to slip out to the left. So friction will be to the right. And the wall is going to exert another normal force. I'm going to call it N star. Okay, so these are the forces on a ladder. Now this is with nobody on the ladder yet. We'll talk about that later. So we need to figure this out. First of all, the sum of all the forces in the x direction must be equal to 0. That means x direction, frictional force, must be equal to N star. I don't know either one of those. I suspect that I will need to know the frictional force to answer the question, will it slip? That seems to be the kind of force I need to know. So this probably will be an equation that I will use later. Let's now look at the y direction forces. All right then, y direction forces, up and down. Well, upwards force, normal, must be equal to the downwards force, mg, and we have those numbers, so that's going to be 25 times 10, or the normal force is 250 newtons. Well, we have our first solution here, a number for a force we didn't know before. And now it's time to look at the torques. Where would you like to choose your pivot point for analyzing torques? Me too, right down here. Natural pivot point for the ladder, and two unknown forces are at that point, so we're going to get rid of them in our torque equation. Very good. Let's see now. Okay, so from this point, we have one force that's going to try to spin the ladder in a clockwise sense, and we have another force up here that's going to spin the ladder in a counterclockwise sense. So now we need to know mg acting at a distance of 4, and we need to know the sign of this angle in here. Now, is this angle in here the 30-degree angle or the 60-degree angle? Well, from the looks of it, it looks very small. It looks like the 30-degree angle. And in fact, by just juxtaposing it with this picture, you can see that this force of gravity is parallel to the wall. and that the picture of our ladder is, of course, parallel to the ladder. So this must be the 30-degree angle. So we're going to take the sine of 30 degrees. So there's a 30-degree angle in here. Then pulling the other way is going to be the n star force, and that's acting at the full distance 8. And now we need to know the sine of its angle. And I suppose you can guess that it's the 60-degree angle from what it looks like. But of course, this n star is parallel to the ground, and this ladder is this direction, and so there is going to be a 60-degree angle. But word finding difficulty, that's a bad sign. That's mainly because I haven't had a single sip of my coffee yet today. And that's because my coffee is boiling freaking hot. Awesome. That's the downside of pour over coffee. It doesn't cool off. All right, we have all of our pieces in place here. We figured out that mg, the weight of the thing, was 250. So we need 250 times 4, which is 1,000. 1,000 times the sine of 30 equals n star times 8 sine 60. So our math is going to be 1,000 sine 30, and then that's 500. Of course, it's 500 divided by 8 and divided by sine of 60, and that's going to be n star is 72.1. Okay, 72.2 newtons. That's the next thing I learned. Well, I know both of the normal forces in this problem. Ooh, and then back over here, of course, we know that F must be equal to n star, so it must be 72.2 newtons. So the question is, will it slip? What do we have to do to determine whether something's going to slip? Well, we have a desired frictional force of 72.2 newtons. But what is the maximum frictional force that we can come up with? Well, that's going to be our coefficient of friction times the normal, which is going to be 0.5 times 250. So it looks like our maximum friction force that we can get is 125. It will slip if we need more than 125 newtons worth of friction, but we only need 72.2. We need less than half of the maximum amount. This will not slip. So this is difficult because we have to do all three of the elements of equilibrium. We had to suss out what some angles were, and it was kind of difficult to do so. There are many different ways to do this. You can also imagine moving the ladder hither and yon and figuring out what happens to these angles. We then had to figure out what a frictional force was and compare it to an external standard of the maximum static friction. Okay, a couple things I want to say about this, just for education and enjoyment. First of all, ladders have these feet on the bottom, so if you set the bottom on concrete, you want to make sure the feet are level and have the rubber pad on the bottom to maximize the friction. If you are setting the ladder into dirt or mud or something like that, flip the feet up. They have a sharp spiky end that punches into the ground and dramatically increases friction, actually trading it for another normal force. That's a safety moment from me to you. Why? You don't want this end to slip. This end not slipping is not 100% guaranteed. What happens when we put a person on the ladder? We put a person on the ladder, the normal force will go up because the weight goes up. N star will go up because the weight of the person will be added to this torque equation, and that means the necessary friction will go up immediately. So what works for just the ladder leaning against the wall may not work as soon as you set foot on the ladder. And it's even worse than that. The higher the person travels on the ladder, the more the N star becomes because of the fact that the torque from the person's weight is moving further and further from the pivot point. As N star becomes more, the friction becomes more. The friction demanded becomes more. So the friction that allows you to get on the ladder here at the bottom may not be enough by the time you get to the top, and the ladder may slide out from underneath you. It's a real problem. These ladders are very dangerous, and they have a tendency to dump you when you're as high off the ground as you can be. There is another way to fail on a ladder, and that is to make the ladder too close to the wall, and then when you step onto the ladder, your weight is actually on one side of the ladder, and the ladder, when you first get on it, will pull away from the wall, and you'll fall over backwards. That particular problem becomes less and less as you climb, so it is not the dominant mode of failure for ladders. The dominant mode of failure for ladders is the bottom slipping out as you get to the top. The other mode of failure for ladders is something that we talked about when we talked about stability. and this is probably the most common household accident. Somebody's on a ladder, leaned up against the side of the house or the eaves of the house, and they're clearing leaves from the um, gutter, or they're putting Christmas lights up or something like that, and the person decides to lean out to grab something. And as soon as their center of mass gets outside of the point of support, the ladder tips over this way. That is probably the most common ladder accident. Ladders are the #1 injurers of homeowners. You would think it would be electricity or something like that, or garage door openers, or garbage disposals, but no, apparently it's ladders and has been for a lot of years. All right, we're going to do a few of these ladder problems in the homework, but now you've seen me do it. Pass this around. I'm going to upload this and get my day started.